Hello, welcome back. In the last few classes, we were discussing about the inert gas atoms or inert gas crystals. So that we have attractive interaction and repulsive interaction in the case of inert gas atoms. So attractive interaction is in the form of van der Waals force or van der Waals interaction, and repulsive interaction we have seen the potential of the form B by R raised to 12. Okay, and attractive interaction is of the form A divided by R raised to 6. So this is the interaction between two atoms in a inert gas crystals. Okay, so we have calculated total energy, that means total binding energy or total cohesive energy. Okay, so instead of this, another empirical form for the repulsive interaction is the interaction UR is equal to lambda exponential minus R divided by rho, where R is the nearest neighbor distance. Okay, so this is exponential. This potential is exponentially decaying. Okay, when rho equal to R, then UR become lambda divided by E. E raised to minus 1, that is lambda divided by E. So this is exponentially, this is 1 by E of the potential become 1 by E of the original potential. That means rho is a measure of the range of the repulsive energy or repulsive interaction, is the measure of the range of repulsive interaction. Okay, so this is 1 by R raised to 12. The other one is exponential e raised to exponential R divided by rho. Okay, where rho is the range of the rho gives the range of the potential. Okay. Let us now talk about the ionic crystals. These ionic crystals are made up of positive and negative ions. So these crystals are made up of positive and negative ions. One example of the common example is NaCl, potassium chloride, then cesium chloride. These are the examples for ionic crystals. So here in NaCl, Na plus and Cl minus ions are. So we have seen the structure of NaCl and CSCl in the first chapter. Now let us talk about the electronic configuration of these ions. So the important thing is in NaCl, the electronic configuration of this Na plus and Cl minus is similar to that of the inert gas atoms. Okay, that means they have closed electronic shells. Outermost shell is closed one. So let us see what is neutral Na. Neutral Na atom has electronic configuration. So Na the atomic number is 11. 11 is the atomic number of sodium. So 1s2, 2s2, 2p6 and 3s1. Similarly, Cl atom. Cl is 17. So 1s2, 2s2, 2p6, 3s2, 3p5. So this is the electronic configuration of Na and Cl, neutral Na and neutral Cl atom. These are the. Next, the ionic sodium, that is Na plus, has so lack of one electron. So 1s2, 2s2, 2p6. So one electron has gone. And chloride ion, that is Cl minus, has 1s2, 2s2, 2p6, 3s2, 3p6. So this one electron goes to this thing. So this become Cl minus because it has only 17 proton but 18 electron. Here 11 proton but 10 electron. Okay, so that is why it is Na plus and this. So here the electrostatic interaction between positive and negative ions. So that is the cause of the ionic bond. So ionic bond results from the electrostatic interaction of oppositely charged ions. Now the charge distribution on each ion in ionic crystal have approximately spherical symmetry. So this is similar to, as we said, it is similar to the that of, so the electronic configuration is similar to inert atom, inert gas. Okay, so what is this inert gas? This is the configuration of 1s2, 2s2, 2p6. This is the configuration of neon, and this is the configuration of argon. So it is similar to that of inert gas. Okay, so they have spherically symmetric electronic distribution or charge distribution around the nucleus. So it is approximately spherical symmetric with some distortion near the region of contact with the nearest neighbors. Okay, so that picture is given in the textbook. Now let us see what is the electrostatic or Madelung energy. Now let us consider a crystal in which there are large number of positive and negative charged ions. The long range Coulomb interaction between ions with charges plus or minus q is equal to, the interaction potential energy is equal to 1 by 4 pi epsilon 0 plus or minus q square by r. Here plus sign is for the interaction between like charges, plus q and plus q. Similarly minus q and minus q. If one charge is plus q and the other charge is minus q, then it will be minus q square by r. Okay. The repulsive interaction between ions with the inert gas configuration. So we are talking about the ions. These ions are having the configuration of inert gas. So the repulsive interaction between these ions with inert gas configuration are similar to that between inert gas atoms. So in inert gas atoms we have discussed already. The repulsive energy is B by R raised to 12. Okay, but we are not using this thing. We have another empirical formula for this potential. UR is equal to lambda exponential minus R divided by rho. This is another empirical form for the repulsive interaction. Okay, so it is widely used, the repulsive interaction. Now the ions have the electronic configuration similar to that of inert gas atoms. Therefore, there will be van der Waals interaction as well in this ionic crystals. But it is only about 1 to 2% of the total cohesive energy. So it is insignificant. Okay. The main contribution to the binding energy is actually the electrostatic energy, and this is called Madelung energy. Okay, so the main contribution to the binding energy in ionic crystals is the Madelung energy or the electrostatic energy. So that is what we are going to find out now. Now let us consider the interaction potential between two ions, a reference ion I and another ion J. Okay, so the potential, if this is the Uij is the potential energy between these two. Okay, then the total interaction energy of ith ion, that is Ui, is equal to, so there are large number of ions surrounding this ith ion. So we have to sum this potential over all jth ion. Okay, summation Uij. So this is the energy of ith ion. So ui is equal to summation uij. Okay, here what is uij? It is equal to uij is given by uij is equal to lambda. The repulsive potential is lambda exponential minus r. It's actually distance between this two is rij divided by rho. Okay, plus or minus 1 by 4 pi epsilon 0 q square by rij. So the distance between these two is rij. Okay, so then the potential is this part is repulsive part and this part is the electrostatic part. Okay, so this is due to the electrostatic interaction. Okay, it may be plus or minus. If this is like charge, and then it will definitely this will repel, and if unlike charge, this attracted. Now for a crystal of n molecules, if we can consider, if the crystal has n molecules, that means one molecule, for example NaCl, this is one molecule, so there is two ions. Okay, so n molecules or 2n ions. Therefore the total interaction energy U total is equal to total cohesive energy U total is equal to n times Ui. Here there are 2n number of ions, but we have used n because we have to count each pair of interaction only once. Ua is the interaction of one ion. Now we have to take n independent ions. Therefore total energy is n times Ui. This is equal to n times Ui is the sum of Uij. Uij has two terms. This is the first term is the repulsive term, which is effective only among the nearest neighbors. So if there are z number of nearest neighbors, so we can write this sum is z times lambda e raised to minus. So the nearest neighbor distance is r divided by rho minus 1 by 4 pi epsilon 0 summation plus or minus q square by r ij. This is equal to n times z lambda e raised to minus r by rho minus 1 by 4 pi summation j plus or minus q square by this rij can be written as pij into r. In terms of the nearest neighbor distance, this rij can be written as pij into r. So this again can be written as n times z lambda e raised to minus 1 by r minus. So this summation plus or minus 1 by pij can be written as alpha. So this is 1 by 4 pi epsilon 0 alpha q square by r. Okay, here alpha is equal to summation 1 by plus or minus 1 by pij. Okay, so this is the quantity alpha, constant called alpha. This is the constant alpha, which is called Madelung constant. Okay, so Madelung constant is the quantity comes in this summation, which is equal to summation of 1 by pij. So this p plus comes for the interaction of like charges individual pair. Okay, and minus comes for the unlike charges. At equilibrium separation, the nearest neighbor distance now will be r is equal to R0. Then what happens? So we can differentiate this thing, this potential. du total divided by dr will be equal to 0. So this, the potential energy will be minimum, that is du by dr is equal to 0. Therefore we can write this thing as differentiating this thing n times that lambda e raised to minus r by rho into minus 1 by rho minus 1 by 4 pi epsilon 0 alpha q square by r square into minus 1 is equal to 0. This can be written as in r is equal to r0 at minimum potential energy. Okay, so that is the equilibrium. Therefore, we can rearrange this equation. R0 square exponential minus R0 by rho is equal to 1 by 4 pi epsilon 0 rho alpha q square divided by z lambda. Thus the total lattice energy ion crystal of 2n ions at their equilibrium separation u total is equal to nz lambda e raised to minus r0 by rho minus n divided by 4 pi epsilon 0 alpha q square by r0. So using this above equation of r0 square exponential minus r0 by rho, in this we get exponential minus r0 by rho can be replaced from this equation, that is n z lambda into 1 by 4 pi epsilon 0 rho alpha q square by z lambda r0 square minus divided by 4 pi epsilon 0 alpha q square by r0. This can be simplified into total is equal to minus 1 by 4 pi epsilon n times alpha q square by r0. I take this common to both the terms, therefore this will be 1. Second term, the first term minus rho divided by r0. Okay, this term minus 1 by 4 pi epsilon 0 n alpha q square by r0, this is called the, this is some energy, this is called the Madelung energy. Okay, so Madelung energy is the, it is 1 by 4 pi minus 1 by 4 pi epsilon 0 n alpha q square by r0, where alpha is the Madelung constant. Okay, so here rho is of the order of zero point 0.1 r0, so that the repulsive energy is short range, the repulsive force is short range. Okay, so in the next class we will discuss how to find out the Madelung constant. The evaluation of Madelung constant will be discussed in the next class.